Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be continuing our discussion on the free motion of an asymmetric body. So let us recap few results. So free motion of an asymmetric body. Okay, so we recall that we found out that the various conservation laws can be geometrically represented with the so-called spheres and ellipsoids. So we saw that the momentum conservation or the angular momentum conservation could be written in the form of an L sphere as follows, where Li's are the angular momentum about the three principal axes of the object, and this is a constant. L square is a constant. So this we called it as the L sphere. And then similarly the energy conservation could be written as the so-called T ellipsoid in the form of an ellipsoid, L1 square plus A by A, L2 square by B plus L3 square by C is equal to 2T. This is another constant. T is the total kinetic energy, and where A, B, C are the so-called moments of inertia. Right? So we have this is in the form of the so-called T ellipsoid. Okay, so then we look at some specific cases of these conservation principles. The first one is, so we talk about the trajectories of the particle or the so-called phase paths. Okay, so now assuming that the moment of inertia can be ordered, so we assume that the various moments of inertia of this asymmetric body, A is less than B is less than C, and we also assume that L is fixed. So the total angular momentum of the body is fixed. So now the conclusion that can be drawn from this statement is that the kinetic energy T cannot be too small or large. This is based on the conservation of energy or the kinetic energy, because now my kinetic energy will be lying in the range from L square by 2C to L square by 2A, where this one is T min. L square by 2C is the minimum value of the kinetic energy, and L square by 2A is the maximum value. Okay, so then we can further look into some specific cases. So suppose we have T is the minimum kinetic energy. So suppose T is T min. So then we expect that the intersection of the L sphere and the T ellipsoid, they occur at 2 points. So the conclusion is that the intersection of the T and the L curves, the T ellipsoid and the L spheres, occur at 2 points 0, 0 plus minus L, and they correspond to the steady state or the steady rotation about the gx3 axis, right? So we see that the intersection, if our kinetic energy is the minimum value fixed, then the two curves, the ellipsoid and the sphere, they intersect at these points 0, 0 plus minus L, implying that we will have the rotation about the the x3 axis, the x3 principal axis, right? Okay, so then so similar conclusion can be drawn. For example, if T is L square by 2b, then the curves, the intersection occurs at 0 plus minus L0, and in that case we have that the rotation is about the gx2 axis. The rotation is about the gx2 axis, and if we have similarly, if we have the intersection T is the maximum value L square by 2a, then of course we can conclude that the intersection is at plus minus L comma 0, and then the rotation is about the gx1 axis. Okay, so then we can look at the stability of these rotations about the principal axis. So for example, the stability of the steady rotation about the principal axis, So we see that the steady rotation we are talking about an asymmetric body. So of an asymmetric body will be stable about each axis with the largest and the smallest moments around the principal axis gx1 and gx3. So the steady rotation of an asymmetric body about the principal axis is stable for the axis with the largest and the smallest moments. Okay, so we are talking about the gx1 and the gx3 axis respectively, and it turns out that the stability always alternates. So we have found two stable axes, which means the axis in between, the gx2, will be unstable. So so this will correspondingly imply that instability around about the gx2 axis. Okay, so then we can further, add, if we do a proper stability analysis, perhaps we could add some damping, like we do in the motion of simple harmonic motion of a pendulum. If we add a damping, we see that in this case as well, corresponding to the SHM, simple harmonic motion, the damping will reduce the kinetic energy, and the kinetic energy will go to the value which is the minimum, or T min, which is L square by 2c. So in the presence of damping or presence of energy dissipation, we expect that the body will end up rotating about the principal axis with the largest moment of inertia, and end up rotating about the principal axis with the largest moment of inertia, and this corresponds to the smallest kinetic energy. Okay, so then what about the motion of the body about this principal axis? We need to say something on that lines as well. So what we are trying to focus now is the motion of the body. Suppose we have already solved the Euler angles, right? and we have found the solution to the Euler angles, or we have found the omega i's. So suppose the Euler angles, Euler's equations have been solved for omega 1, omega 2, omega 3, right? They have been solved, and then the question is what is the corresponding motion of the body, about the E1, E2, E3 frame, right? So we want to find out that, right? So these are my principal axis for the body fitted frame. So this is the principal embedded frame, or the principal axis about the body fitted frame. Principal embedded frame. Okay, so we see that if we were to find the time variation of the EJ in the inertial frame, right? So inertial frame implying the fixed frame. In the inertial frame, so we see that in this case EJ dot is omega cross EJ. EJ dot is omega cross EJ, and if we were to expand this vector equation, we see that we will end up with three equations. E1 dot is omega 3 E2 minus omega 2 E3. E2 dot is omega 1 E3 minus omega 3 E1, and E3 dot is omega 2 E1 minus omega 1 E2, right? And we see that we can solve this set of equations either numerically, or we can solve this approximately, right? So we call this as my equation set of star. Okay, so then the answer lies is, so the motion of the body, the free motion of the asymmetric body will be described by these equations, which is the standard equation of the motion of the principal embedded frame. Okay, so then let us look at an example. So the problem says an asymmetric body is in steady rotation about the principal axis with the largest moment of inertia. So we need to find an approximation to the wobble of this principal axis if the body is slightly disturbed. Okay, so what we have is, we can assume that the moment of inertias are ordered for this asymmetric body, and such that we have also assumed that the angular velocities are such that omega 1 and omega 2 are 0. So the body is purely rotating about the gx3 axis, and the rate of rotation is constant. Let us say with the rate capital lambda. So this is a constant. Okay, so in the disturbed motion, we see that omega 1 and omega 2 and of course their time derivative omega 1 dot and omega 2 dot, they are small. So when we perturb the system, we expect that there is a small variation about this gx1 and gx2 axis, or the so-called wobble. So we linearize the Euler's equation accordingly with these small variations in omega 1 and omega 2. So linearizing, we see that a omega 1 minus b minus c omega lambda omega 2. So lambda is omega 3, this is 0, and b omega 2 dot minus c minus a times lambda omega 1 is 0, and c omega 3 dot, this is also 0. So these are my three sets of equations. I can quickly, here I see that omega 3 is a constant. I can plug it. We can solve these two equations, the first and the second equations, independently, and we find that omega 1 is p times cos of omega t minus gamma, and omega 2 is p times sine of omega t minus gamma, where p is my amplitude given by lambda times square root c minus b by a, and my omega, which is also given by the frequency omega is given by lambda times c minus a times c minus b divided by ab to the power half. Right? So these are my constants, and from here I can quickly find that my angular momentum L1 is a omega 1 and L2 is b omega 2, and from here we can find out what is the position of the various body fitted frame EIs. So what are these? So what we have to find, we need to find the motion of the body. That is, we want to find the motion of the body fitted frame. So to find the actual time variation of the unit vectors Ej, we have that E1 is cos of omega t times I and plus sine of lambda t times j, right? And E2 is minus lambda t times I plus cos of lambda t times j, and similarly E3 is k, right? So these are my various body fitted frames, and we can see that from here we can quickly see that E3 dot is omega 2 E1 from the Euler equation minus omega 1 E2, and if we plug this, we will get that omega 2 times cos of lambda t I plus sine of lambda t j minus omega 1 minus sine of lambda t I plus cos of lambda t j, and we see that if we substitute my omega 1, omega 2 and omega 1, we get back, this is from the linearized equation, equations, which is my star, I think. No, we haven't named. So let me call this as linearized equation 1. So linearized equation 1, we can find the by plugging these omega 1 and omega 2, we can find the approximate or the linearized wobble about the E3 axis, right? So linearized wobble about the GX3 axis, and that is what we wanted. So the final answer is that E3 E3 will be equal to the highest order is k, order 0, plus then we will have the order epsilon terms, which is coming from this linearized approximation, which has a frequency of omega plus minus lambda, right? And in this case, the motion is not periodic. The motion is not periodic. We see that in this case, omega plus lambda and omega divided by omega minus lambda is typically not rational, right? If it is rational, then the motion is periodic, which will be the LCM of these two numbers, and typically that is not the case, and this is in general. And if this is the case, that we have this ratio irrational, we expect the motion to be aperiodic, or we don't expect the phase paths to be closed. The trajectory is not closed. Okay, so I think in terms of theory, we have seen enough, and we can now look at one specific case of the motion of a rigid body. How to solve the motion using the Euler's equation of motion. So let us come back to the so-called very innocent looking the motion of the rolling wheel. Now the rolling wheel seems to be a very simple object where we have the motion of a disc rolling on a floor, and we expect that the motion will be very quickly determined. But as we shall see when we look at when we include the 3D motion of this wheel, including the translation as well as rotation, involving the Euler's equation of motion, we will see how complicated this motion becomes. So let us look at the case of the rolling wheel. The rolling wheel. So let us draw some diagrams so that it's easier to refer the motion. So we have a wheel which with its axis perpendicular to its surface as A, and then the axis along the wheel is N. So N is perpendicular to A, and then we have the perfectly vertical axis K, and we expect that the weight of the wheel is minus mg along the k minus k direction, and this N axis makes an angle theta with the wheel at any given point of time. So then we expect that the wheel is also going to make an angle. So it is not exactly moving horizontal to the inertial frame. It is making an angle, let us say an angle phi, and let me rename this as axis z, and this is my axis y. So here are it seems now here is everything that we need to demarcate for this wheel. And then at the point of contact, we can assume that there is a normal force or there is a reaction force. We call this as the force vector x. And then this question now we want to answer is that suppose a wheel is free to roll on a horizontal floor, and this question is how does it move? So we have drawn everything we needed to draw for the wheel, and typically we expect the wheel to exhibit a motion having non-holonomic constraints, because we are involving the velocity in the constraints, as we shall see soon. So what I just said is that the motion of the wheel has non-holonomic constraints in the language of calculus of variations. So non-holonomic constraints, and which means that it cannot be solved using the Lagrangian method. Lagrangian method. It can't be solved using the Lagrangian method. So we can assume that we have a disk. The wheel is a disk of mass m, and we can further assume the radius is b, and it is rolling in the xy plane. So rolling in the xy plane with contact point C. With contact point C. Right? And we expect that, let us say our axis A is A of t, which is the axis of the wheel about which the wheel is rotating. And this is the so-called axial unit vector. Axial unit vector. And then we can assume that n, the vector n, which is also changing with time. So n of t is the unit vector, unit vector along the perpendicular to A, or along the CG axis, or along the CG direction. CG direction. Right? So G being the center of mass, so G is the geometric center. So n is the unit vector along the CG direction. Okay, so then let us say that the angular velocity omega is a cross a dot. This is what we had found earlier when we were looking at the motion of a top, and we found that the angular velocity omega is a cross a dot plus lambda times a, where lambda is the spin. Lambda is the spin, where lambda is omega dot with a. So this is the spin, right? And we see that the corresponding angular momentum Lg is given by I times omega, right? So where I is a times a cross a dot plus c times lambda a. So these are my smallest and the largest moment of inertia about the axis, principal axis. Okay, so then we can write down the various equations of motion of the body. The first equation of motion is the equation for translational motion. So for translation we see that m times dv dt is x minus mg k. So we have the x being the normal reaction, and mgk is the weight of the object acting along the negative k hat direction. So the vector x already includes the direction, so we don't need to worry about the direction of this unknown reaction force. So then for the rotational motion, so this is translation. So for rotation, we see the following equation of motion. We see that the rate of change of angular momentum, so ddt of a times a cross a dot plus c times lambda a is equal to minus bn cross with x, and this is where b is the radius of the object, the wheel, and x is the force which is providing the torque about the center of mass axis, the g axis, right? And then we also would like to impose the rolling condition. We have, remember in the problem we have assumed that the wheel rolls, not slips. So the rolling condition at point C, right? If we look at the diagram, the rolling condition has to be applied at point C. So at C we see that V plus omega cross minus Bn is 0, right? So this is the net velocity at point C. And if we now we have three equations and we have three unknowns. The unknowns are x and v and omega. So if we eliminate x and v, eliminate the reaction force x and the velocity v from these three conditions A, B, C, we see that ddt of A cross A dot plus C times lambda A plus mb square. We have eliminated everything except the unknown omega. So omega dot minus omega dot n times n minus omega n times n dot, right? So all these quantities plus mb g times n cross k, this is equal to 0, right? So these are this is the giant equation we get, which is for omega, for the unknown omega, which is the angular velocity, right? So let me call this as equation number D, this giant equation. And now what we expect now is to further determine the motion. So one thing I wanted to highlight from the diagram, notice that the axis of rotation A and the normal axis N, they are not independent. They are all associated with the body of the wheel, which is a body fitted frame. And we expect that, so A and N are not independent. And in particular, we can find out N from A. So N is K minus K dot A times A divided by K minus K dot A times A. And notice that we have found this relation with the so-called Gram-Schmidt orthogonalization process. And this is a simple setup. We call this equation number 5. So that is how N and A are related. So now if we use 5 to eliminate N from equation number 4, right? So not 5, but I should maintain the homogeneity. I should call this equation number E. So what I am doing is using equation E to equation D to eliminate N, right? And then we will purely get an equation involving omega and A. Now we can write down the various components by taking the necessary dot product with the quantities to simplify our new set of equations. So this is eliminate N in equation D, right? The giant equation. Now if we take the dot product, so taking the dot product of equation D with respect to A, N and A cross N, right? These are my various three vectors. We see what happens. So we will have, with all these three sets of equations, we will get three new equations. So C plus mb square lambda dot minus mb square triple product of A with A dot with N times N dot comma A. N dot with A, and this is equal to 0. And then the second one is A times triple product of A comma A double dot comma N plus C times lambda times A dot N. This is 0. And then the third equation we are getting by taking a dot product with A cross N. We see that this is A plus mb square A double dot with N minus C plus MB square, scalar triple product of A dot, N minus MB square, A dot, N times A N dot. Okay, and minus GMGB times A dot with K, and this is equal to 0. Now let us now go back to again the referring diagram and try to utilize the angles. See, in our equation we had introduced two angles, theta and phi. So what is phi and what is theta and what is phi? So theta is the angle between the plane of the disk and the vertical k. So it is we see the angle. So theta is the angle between the vertical k and the plane of the disk, which is, so theta is n dot with k. So we see that similarly phi is the angle between the tangent to the disk and the horizontal axis. So it is the angle between the tangent to the disk and the OX axis, the tangent to the disk and the OX axis. And we see that in this case we get A to be cos theta sin phi I hat minus cos theta cos phi j hat plus sin theta k hat, right? And we see that N is minus sin theta sin phi I hat plus sin theta cos phi j hat plus cos theta. So this is purely from geometry that we have written these two vectors. So now we call this as equation number 6, not 6 but F. Now we can we have now the complete liberty to use this F. Now the axis A and N now are completely defined in terms of the angle. We can plug it into the set of three equations that we had seen, which was originally written in the form of A and N, and now we can have the new set of equations described in terms of theta and phi. So what are these? So we see that, so using our equation F, we see that the new set of equations are C plus MB square lambda dot plus MB square cos theta phi dot theta dot, this is 0, A times cos theta phi double dot minus 2 sin theta dot phi dot and plus C lambda theta dot is 0, and then A plus MB square theta double dot plus A cos theta sin theta phi dot square minus C plus MB square lambda cos theta phi dot minus mg b sin theta. And these are my set of three equations that we have found using the angle. So now the unknowns in this set of three equations are theta, phi and the spin component lambda. And why lambda is an unknown? Because typically lambda is not a constant. You will see that readers will see that they are in general a function of time. So now we have found out the set of linearized equations governing the full motion of the body, in this case the wheel, and we can solve this set of three equations to eventually find the complete motion of this rolling wheel under the non-holonomic constraints, right, of the rolling condition. So I will not specifically solve this equation, but I will leave the listeners at this point. This is pure algebra, and this concludes our this example also concludes our discussion on the motion, the general motion of the rigid body. Now, in the next module, we will see that we have seen, let us now briefly recap. So far, we have seen how to solve problems in classical mechanics using Newtonian mechanics. Then later half, we also saw how to solve problems using the calculus of variations or the analytical mechanics. And now in the next module onwards, we will see yet another way of solving problems, the way of so-called the dimensional analysis and the scaling. So thank you so far for listening.